In this video, I want to talk about finding the domain of a function, but only for two special cases: when x is in the denominator of the function and when x is inside of a square root. For example, here I have a function where x is in the denominator. Remember, the denominator cannot equal 0, so there may be some values of x that would make that denominator 0, and I need to find out what those values are. So let's take our denominator and set it not equal to 0 and solve for x. We can solve by factoring. And we'll find out that x cannot be -4 and x cannot be +1. If I write this domain in interval notation, I could have values off to -infinity, all the way up to -4, but not including -4, in union with values from -4 to 1, but not including -4 or 1, in union with values from 1 to infinity, not including the 1. If we look at a graph of this function, the graph would look something like this. Notice from left to right that x values are being used all the way and being graphed all the way until we reach -4. Then we have a vertical asymptote at -4. So x cannot be at -4 back in our function. Then we have values graphed from -4 to 1, not including -4 or 1. Ignore that vertical line in the graph, that shouldn't really be there. And then we have values to the right of +1. Let's look at a second example. G of x equals the square root of x plus 5. In this case, x is inside of a square root. The value inside of a square root for real numbers must be greater than or equal to 0, so let's just say that that radicand must be greater than or equal to 0. This is a little different than what we did a little while ago with the fraction, because in that case the denominator could not be 0. In this case we're saying the radicand has to be greater than or equal to 0. If we solve this, we get x is greater than or equal to -5, which in interval notation would be from -5 off to infinity, including -5. Let's look at a graph of this function. Here's the graph of that square root function. Notice from left to right, nothing's being graphed to the left of -5, but as soon as we reach -5, we graph the x values from -5 off to infinity. Let me give you a problem to practice. Pause the video, find the domain for this function, and then come back to the video to check your answer. Once again, the denominator can't be 0. So let's solve for x. We can factor, setting each factor not equal to 0, and solving. So we find that x can't be 9 or -3. In interval notation, that would be represented as -infinity to -3, in union with -3 to 9, in union with 9 to infinity. Looking at a graph of this function, from left to right, we have values from -infinity up to -3, not including -3. Once again, ignore that vertical line, that shouldn't be there. We also have values from -3 up to 9, not including the 9. We have vertical asymptote there also. And then values from 9 to infinity. And let me give you one more practice problem. Pause the video, determine the domain for this function, and then come back to the video to check your answer. In this case, x is inside of a square root. The square root, the value inside the square root has to be greater than or equal to 0. If we solve for x, we find that x has to be greater than or equal to 2. In interval notation, that would look like this, from 2 to infinity, including the 2. If we look at a graph of this function, we see that the domain, that nothing happens before 2, but once we hit 2, we start graphing the x values from 2 off to infinity. Once again, this is the process of finding the domain for only two special cases. The case in which x is in the denominator and the case in which x is inside of a square root. The graph can help you see the domain, but be careful because graphs can sometimes be deceptive.